In order to compute the page rank, we have developed a mathematical model for a random server on the World Wide Web. The probability of going from one page to another is given by the Google metrics. By repeatedly multiplying with the metrics, we can get from every page the probability that the server ends up on that page. In this video, we will look in more detail at the mathematical aspects of this model. The PageRank vector is computed by multiplying with the Google matrix A infinitely many times. This Google matrix models two types of transitions between pages. The random server can follow outlinks, the first term in the definition of A, or can teleport to another page, the second term in the definition of A. Several questions come to mind when looking at this iterative process. First, to which vector does this process converge? Second, is this vector independent of the initial vector? And third, does the vector that we find still correspond to a probability distribution? This means, does it have values between 0 and 1? And do all the values add up to 1? The first two questions are relatively easy to answer. The repeated multiplication of a vector with a matrix is called a power iteration. It makes the vector x point more and more in the direction of the eigenvector. And the power iteration is the simplest algorithm to calculate the largest eigenvalue and the corresponding eigenvector of a matrix. If the largest eigenvalue is unique, the corresponding eigenvector is also unique. Of course, up to a scaling constant. The process converges to this unique vector for any initial guess that is not orthogonal to this eigenvector. This means that your initial guess should have some component in the direction of the eigenvector of the largest eigenvalue. This is hardly a restriction. In fact, any random vector is almost certainly not orthogonal to a given vector. The question whether this eigenvector corresponds to a probability distribution is more difficult. If it corresponds to a probability distribution, it means that it has to be real and that the eigenvector can be scaled such that all its entries are positive. Fortunately, our matrix A has some properties that guarantee this. First of all, the matrix is positive. All its entries are positive. Such matrices have a unique real largest eigenvalue and corresponding positive eigenvector. By scaling the eigenvector, we can make it such that all the entries add up to 1. These properties are guaranteed by the so-called Perron-Frobenius theorem. To give some intuition why these properties hold, if you start the power iteration with a positive vector, then all subsequent vectors will also be positive because all entries of A are positive. And we already saw that the power iteration converges to the eigenvector that belongs to the largest eigenvalue. What we did not show yet is that the largest eigenvalue is unique. In our case, where A is stochastic, meaning that the columns add up to 1, we even know the value of the largest eigenvalue. It is exactly 1. Now we know, in principle, how to compute the PageRank vector by the power iteration that will give us the eigenvector that belongs to the eigenvalue 1. To do this, we have to decide when we can stop the iteration. A simple criterion to do this is when the power vector x does not change between iterations more than a small tolerance. The main computation cost of the algorithm is the matrix vector multiplication with A. Clearly, this should be done with care, since A is extremely large. So how should we do this? We have an explicit formula for the matrix A. It may have seemed natural to simply compute A and then multiply it with it. This is, however, an extremely bad idea. There are billions of pages. Computing A will give you a matrix with billions times billions numbers. There's no computer now that can store such a matrix, let alone do computations with it. Fortunately, we can make use of the structure of A. We can multiply with the matrices from the outlinks and for the teleportation separately. The matrix P transposed that contains the information about the outlinks only contains a few non-zeros per column, since every page only has a few outlinks. So I only need to store which page is connected with page. And by multiplying with p transposed, takes billions, the number of pages, times a few outlinks per page's operations. Realize that this is billions times faster than multiplying with the explicit computed matrix A. Multiplying with the teleportation matrix is even simpler. Just take the inner product of x with E, the vector with only ones. In fact, not even this inner product has to be calculated. Taking the inner product with a vector that only contains ones just means that you take the sum of all the coefficients of x. If we keep x stochastic, we know this value, the sum is equal to 1. So multiplying with the Google matrix A can be done extremely efficiently. The number of multiplications is equal to the number of outlinks in the World Wide Web. But this is still a very large number, and you have to do this in every power iteration. It is therefore worthwhile to think if there's a faster algorithm than the power method to compute the PageRank vector. It is possible to speed up the calculations. An idea to try to achieve this is to make use of the fact that we know the largest eigenvalue is 1. This knowledge is not yet used in the power method. To solve a standard eigenvalue problem, we have to calculate both the eigenvector and the eigenvalue. But since we already know the largest eigenvalue, and it is 1, the computation of the corresponding eigenvector is not really an eigenvalue problem anymore. It can be solved by rewriting the eigenvalue problem as a linear system. The eigenvalue problem is defined in the first equation, where we have substituted 1 for the eigenvalue. You can see now that by bringing the eigenvector to the left of the equation, we arrive at the linear equation system. In the lab assignment, we will ask you to investigate this method further and to compare it with the power method. In this and the previous videos, you have learned how the PageRank is computed. What is the underlying model? What is the PageRank vector itself? And how can it be computed efficiently? Some people use this knowledge to manipulate their website such that it gets an artificially high PageRank. This can, of course, give important commercial advantages, and in the last video we explain how to do this.